Hello, everybody. Good afternoon, and thank you very much to Copper Alliance and ETHI to let us present this webinar on a new generation of copper conductors for overhead lines. Okay, the first slide, I wanted to show how is the evolution, the historical evolution of the overhead line conductors. You can see here that, and you know most probably that more than 50 years ago, the conductors installed on overhead lines were made of copper. So today there are still a lot of lines built in copper. Okay, so and the history and the evolution makes that due to cost and weight, the evolution was to go to the ACSR conductors, which are aluminum with the steel reinforcements, with a steel core. Okay, after that, they enter in the market the all aluminum alloy conductors, trying to solve weight problems and removing the steel on the core, trying to have the conductor lighter. After that, they appeared the new generation of high temperature low sag conductors, known as HTLS, which try to solve a huge problem that there is today, which is the problem of trying to see if it's possible to increase the power of the lines without touching any tower. Okay, on that scenario, these conductors are conductors which are really special. They are made of special. They are using special cores in some cases, and the cost of this solution is really high compared with the standard solution. With this scenario, we saw that there was a possibility on the new generation of copper conductors. Okay, we realized that the cost was not an issue, and we started developing 4 years ago this solution, trying to see if with these new alloys we will be able to increase the temperature of operation of these conductors, trying to see if we can pass as much capacity as possible. And today I will present the main properties of this new generation of copper conductors. Okay, the CAC is how it's commercially known. Is the copper alloy conductor specially designed for overhead lines. It has two main characteristics. One is the copper microalloy, which is giving to the solution a mechanical and electrical properties, really huge mechanical properties and really good electrical, and the coating. The coating gives to the solution a dielectric property because we are coating every single wire, okay, and on the external part, this coating, it has a property which is the hydrophobic property, which means that the water, when touch the surface of the coating, it goes out. Okay, so with this solution, we try to solve a huge problem on the market. Before starting to the main presentation, I wanted to just show you how is the evolution of this, on what are the main properties of this copper microalloy. Okay, here you can see at the table, you can see the ETP properties. Okay, so on this one, you can see how the ETP, the copper microalloy, it has been improved in a way that just adding 1% or less than 1% of alloy, we can improve and double the braking load, okay, or even more than double, 3 times, and we can increase a lot the annealing temperature. And that's really important because after you will see how is important to have this high temperature in order to transmit more power. And all this one, it's really interesting because the conductivity, of course, it's affected, but it's really not too much affected compared with the solution on the market, which is the ACSR solution, which has a conductivity around 55% YACS. So these copper microalloy are giving an interesting mechanical properties, temperature properties, without losing too much conductivity. At the end of August, there was a session in Paris, the Ziegler session 45, and during the opening ceremony, there was a guest speaker was Terry Boston, the president and CEO of PGM Interconnection, and during his presentation, he showed one slide that it really interests me a lot. He showed the top challenges facing the energy industry. And the two main points, the two first points, was the electricity demand and the extreme earth and space weather. So the CAC, the copper microalloy conductor, is trying to get an answer to these 2 points on the industry. So the question here is, are the new generation of the copper conductors giving answer to these 2 top challenges? Okay, so this is one of the main questions we are going to answer today. The main advantage of the copper microalloys conductors are the following. Now I'm going to enter in each of these 6 main properties that I wanted to show all of you. But it's really important that it can work at high temperature. Due to that, we can transport and increase the capacity of the conductor. As it is copper, we have fewer losses. We only have an homogeneous material, so it's only copper, so it's easy to install. It has some issues to be considered, but in general, it's a really easy installation. It's a lighter conductor, and I will explain you later why. Okay, this is interesting because, as you know, copper, it's heavier compared with aluminum. It's a lot heavier. But here we will show you why, in some cases, the copper could be lighter than aluminum. And finally, the 6th property that I will present you today is the corrosion. So going through the first one, in here, the first one is that this copper microalloy can work at high temperature. What does it mean? It means that it can, in a sustained mode, can work between 150 and 200 degrees Celsius. And that's really important because even if we work at 200 degrees Celsius, there is no creep. And that's a really an issue on the sector because once they are installing the ACSR in some cases, what they are doing is they have to come back to the line 30 minutes after or 1 day after and tension again the conductor to don't have problems of sag due to creep. Okay, so with this solution, as you can see here on the picture, you can perfectly see how the copper microalloy, which is the one in red, it's completely flat over the 3,000 hours. Okay, it's important to remark that this test was performed at 150 degrees and 40% EDS of the conductor. Okay, so it's really in a high strength situation. Okay, and as you can see here, there was no creep, there was no elongation, while the control conductor that we use was an ETP copper that flows really fast. Okay, so in several hours, it flows, as it can be seen on the picture, on the orange line. And as well, it's important to remark that aluminum flows at 80 degrees Celsius. So with this solution, we can guarantee that with 200 degrees working temperature, there will not be creep. So there will be no loss on mechanical properties. And why is important that? It is important because due to this high temperature, we can increase the capacity of the conductor. So in a normal situation, okay, our equivalent of a CAC conductor can transport 2 times more ampacity than the standard conductor. And that's really important for the sector, because without the need of investing in pylons or just reinforcing the towers, they can transport double power, double energy. Okay, and that's as well really good because it has this ability to cope N-1 or N-2 situations. This N-1 means that if there is one line that falls down, then the line that you design has to have the possibility to transport the energy that has fallen down on the other one. So this is an interesting and really interesting solution for the sector. So it's competitive for upgrading of existing lines, okay, and as well, we are doing that with low energy losses, okay. Another important thing of that is that due to this high capacity, one can think that there will be more sag on the conductor. I will explain you later with examples, with business cases, why that is not happening. So, in some cases, we could have even less sag than in an ACCR solution. And that is really good for the new lines because we can reduce the number of towers or make the towers smaller, or have towers with less steel because there will have less tower tension. And that's really interesting if we analyze that, taking into account the losses. So as I explained you at the beginning, the CAC solution is a combination of 2 main characteristics, the coating and the copper microalloy. So the combination of this dielectric coating and the copper is giving us a lot less power losses. So it's really efficiency. We have 60% more conductivity than aluminum, the standard aluminum. And if we compare it with the ACSR, it could be even more. It could be even 70% more. The dielectric coating reduces a lot the skin effect, and that gives us approximately, depending on the solution and the stranding, that we can increase more than 10% the conductivity. As we are putting as well this coating, and we can play with the thickness of the coating, we can, in some situations, reduce the corona effect. You know that the corona is happening mainly, it's due to diameter of the conductor. As we are putting this dielectric around the external it's as well applied in the external part of the conductor. The electrons are not, it is not as easy for them to go out when there is humidity outside and the corona is reduced. That means that, for instance, if we can, if there is one line that is operating, for instance, at 220 kVs, with this solution, we can reduce more than 30% the section without having any problem of corona. And all of that, it's really good because we are following the Article 15 of Energy Efficiency Directive. Okay, so this Horizon 2020 that tries to focus all the developments and all the points to reduce and have more energy efficiency solutions on the market. Another property of the conductor is that it's easy to install. What does it mean? If we compare the CAC, the copper microalloys, with the HTLS conductors, which has cores, steel cores with some grease on it, or there is a steel or there is fiber, carbon fiber on the conductor. It's easy because we don't need to take the core once we install it. Okay, so if we compare it with this HTLS solution, we can say that it's faster. Okay, the only things that you have to consider when you install it is that you have to use copper or steel fittings or tools. You cannot use aluminum ones. Okay, and that's important to not have problems with corrosion. Okay. Another important point is that you have to use compression fittings or make the right compression on the fitting to break the coating and make the correct mechanical and electrical contact. It's important to remark that when you install this conductor, the external layer has to be removed. And all these steps are being done using standard tools that are on the market. There has not been any design done by Lafarga, special design for this conductor. Okay, so here you can see on the right side the kind of fittings that can be used for suspension or for distribution or compression for transmission. Why we are saying that copper is lighter than aluminum? It is 3 times heavier, and so it's shocked. You can say that it's something that is strange. But if you think not only on the initial tension, if you think on how you are designing the lines, you realize that the towers and all your the overhead line engineers are focused to design in the worst conditions. So that means that even if at the beginning the copper microalloy has more weight, when there is extreme situations as showed on the picture, the diameter is having a really important point. So as copper has more conductivity than ACSR solutions or AAAC, what we can do is to reduce a lot the section of the conductor to have the same properties of ACSR, or even doubling the capacity of the ACSR, and that is giving really interesting mechanical properties once there is extreme wind or ice load. We are talking about wind when there is winds around or above 120 kilometers per hour. When it's above 120 kilometers per hour, this solution, there are other solutions that could be better, okay? But with solutions or with situations where wind and ice load are really important, the copper microalloys are really competitive because we have smaller diameter, so the apparent weight is reduced a lot. And there is another property that when you design the line, we don't consider, and our customers as well are not allowed to consider because the standards doesn't allow them to not considering ice when they design a line. But the coating that we apply on the conductor on every strand has hydrophobic properties. So that means that when there is ice or snow accretion on the conductor, this happens in a really slower way. You can see here on the picture that there is this one. This is a test that we perform in real situations. It's done in a site placed in the border between Scotland and UK, and it's called Dead Waterfell site. And this test has been performed with EA technology, and in there we install 3 conductors, 2 copper conductors with the coating, and 1 control conductor without the coating. Okay, so in here you can see that the 2 copper conductors with coating are the green one and the red one. And the control conductor, which was a standard conductor without coating, it's the blue one. So on the graph you can see here, this is the mechanical load that it has the tower, okay, and this one is the period, it's the time. Here above, below, you can see this is the temperature, okay? So here you can see that the temperature is above 0 degrees, and here it's down 0 degrees. So here it's really interesting because you can see how the control conductors when they start to snow, starts to create ice on the conductor. So the tension on the tower was increasing. In some point, it starts to have more snow, which is what we call wet snow, because it was snowing around 0 degrees, and the conductor goes, it was heavier. So you can see here how the ice makes that the load on the tower was higher than on the copper conductor. And you can see here that even that it was a little bit of a creation on the copper conductor, it goes down really fast. While in the control conductor, it goes down, but it takes more time to remove the ice created on the conductor. On the same site, on the same installation in Dead Waterfell, we also made a wind speed test. So it was in wind conditions. We as well monitor the load on the towers, and then here you can see a comparison between the control conductor, which is an aluminum conductor. Here you can see the bending stiffness of the amplitude of the vibration that is happening on the conductor, and here is the limit, the bending limit. And that point, if the conductor goes above this line, it will break. Okay. So you can, if we compare the two tables, like the two graphs, you can realize that this in here is the frequency of the wind. So on the aluminum conductor, you can see that the vibration happens in a wide range of frequencies, while in the copper conductor it was only small range. It was between 40 and 60 Hz, while in the control conductor was between 20 and 130. And that's an interesting property because that is showing as well that the copper conductor has in somehow a self-damping characteristic. Another point is that, as you can see here, even if the amplitude is the same, so we have around, I think it's around 800 micrometers of amplitude in the both cases, the maximum, you can see that in the copper conductor, the limit it's really far. So that means that if we make a kind of extrapolation, the copper can substand, or can the lifetime of the copper it's more than 100 years, while in that situation in the control conductor it can goes through 30, 50, or 60 years old, and then it will break. So this is really interesting. So you can see here how the copper microalloy is reacting against this extreme situation. So in wind, it's really important the copper microalloy, and in ice conditions, it is important to have less diameter because there will be less accretion, but as well, the coating helps a lot to reduce the tension of the towers. So the both solutions on one single conductor are giving us the lighter conductor in extreme situations. As you know, copper avoids corrosion. It's compared with aluminum. It's against corrosion. It's behaving a lot better. If we add the coating on the conductor, we almost eliminate the corrosion. There are studies done in South Africa that they have made tests on real situation. They put ACSR, AAC solutions, and they compared with the copper, and the copper solution was 4 times better than the aluminum ones. So that means that the copper in extreme corrosion or in a corrosive atmosphere, there will be a lot better, will be behaving a lot better, and will take more time to have corrosion. So if we add this coating, we completely eliminate or almost eliminate the corrosion. So that makes this solution ideal for corrosive environments. In fact, we have a project with Endesa that we are going to install a conductor, a CAC conductor, a copper microalloy, in the salt mines here in Spain. To summarize a little bit all the points that we present you today, we can say that the advanced copper alloys are offering to the sector a competitive solution for niche applications. So that means that in severe climatic conditions, when there is wind, ice, or snow, or corrosion, this solution is really good. And as well, if we add as well and this increase of ampacity, it makes ideal for upgrading of existing lines. It has been performed a technical feasibility by DMV Kema that I will just show you the results today after this slide. And you will realize it was done by them, by DMV Kema, so it was an independent company that make this analysis. We have not been involved on the technical issues, so that's important in order to see that how they have focused the copper microalloy on the sector. So you will see that there is an economical benefit of using copper microalloys if you just take into account not only the investment and you take into account the energy efficiency. This copper microalloy solution makes a lot of sense. So now I'm going to enter in the second part of the presentation. I'm going to make explain you 3 business cases. The first will be the one that I explain you right now. I will explain you the DMV Kema business case. After, I will go through 2 business cases, one with extreme wind and another one with wind and ice load. So the first one, it's an analysis that performed DMV Kema. They had they wanted to compare the copper microalloy with an ACSR solution. The ACSR that they considered was the Haug one. It has 280 millimeters square of section, and the ampacity of this conductor is 630 amps. This is the control conductor. So this conductor was compared with the ACSR Eagle and the CAC 185. Both at 80 degrees can transport the same ampacity, but as you can see on the copper conductor, if we work, this conductor works up to 150 degrees, can transport 1,115 amps. So even if the 2 conductors will have higher investment, they will have lower losses. The line that they design is the one that it's shown here. They use the PLSCAD to analyze all the mechanical aspects of the line. It is a 70 kilometers line at 220 kVs. It was a double circuit, and the climatic conditions considered were the standard, the European standards. Okay, and the results that they get, it was really focused on economical part. So here you can see that the Haug solution has a lower investment, but the cost of losses is really high. So you can see the red part is the cost of losses. If we compare it with the ACSR Eagle, you can see that it has been reduced the losses and increased the investment. But even though this one, it's not really a huge step. But if we compare it with the CAC solution, you can see that the investment has been a little bit more, and mainly it's due to the conductor, okay? But the losses are a lot less. So the efficiency of this conductor gave a really interesting solution, because in a payback time of between 5 and 7 years, the investment that you have to do for the conductor will be recovered. if we enter in the business case, the second business case, I will explain you an extreme situation with ice and wind conditions. This is, in fact, yesterday I was in Iceland, and I was meeting Landsnet in order to, well, to discuss about this situation, and they confirm that they have these extreme ice and wind conditions. In Iceland, they have really the transmission grid has an interesting characteristics, because they have to withstand volcanic eruptions, earthquakes, avalanche, lightnings, salt pollution, a lot of accumulation of snow, and high intensity winds. So here I took as a reference an article that it was written by people from Landsnet and engineers in Iceland, and that they just go to the lines and they monitor them. And on that case here, you can see that there was, in one day, they had an ice load of 15 kilograms meter with an ice density of 7 kilograms meter square, and at the same time, they have a wind speed of 32 meters second. That means 115 kilometers hour. So this is really extreme situation. And the ruling span that they have is 120 meters, and the conductors that they are installing are mainly the AAAC conductors of 28 millimeters diameter. So if we make a comparison, this one it's a software that can compare different conductors in a simple way. So here you can see the conductors, you can choose the conductor that you want to analyze, and here you have the properties. Okay, so in that case, what we have is that we select these three conductors, the Drake, the ACCC 470 millimeters square, both has 28 millimeters, and we compare it with the CAC solution of 300 millimeters. So here you can see the properties of each conductor. Okay, these are the general conditions, so these are the conditions that were installed. This is the ruling span that I showed you before. It was between towers, there was 120 meters of ruling span. And here you can see the climatic conditions. So, one of the main things is that you can see that with using CAC, the copper microalloy, you will reduce the resistance, the AC resistance. Okay, so you will reduce the losses. With this wind speed and this ice thickness, you can see here that the tower tension on the copper conductor was the same. And it has an interesting property that it has less UTS. That means that the conductor is farther from their breaking strength. Okay? So you can see here that in the copper solution, the breaking strength was higher compared with the both solutions. And the good thing of this example is that having less resistance, the same tower tension, less UTS, we can get double ampacity, or more than double ampacity. So you can see here how we can transport more double ampacity, and the sag was less, we have less sag than the solution with the ACSR or the AAAC. So this is really interesting. You will have a line where you will have just taking the CAC and installing the CAC, you will have the possibility to transport double energy. And the third and last business case that I will present you is it's the conductor working in extreme wind conditions. I take this case considering a center point energy company. They have in the States, they have wind speeds really, the hurricanes, which are 63 meters second, which is 225 kilometers hour. This is really, you can see here in the pictures, the damage that it creates the wind, this kind of wind on the power lines, though the towers are just falling down. Okay, so instead of using the Drake, I use the Hawk to just show you different conductors. And on that case, the center point, well, the US, the state's norm allows the maximum RVS to be around between 40 and 50%. So with this consideration, we make the same analysis. So we select the conductor, the Hawk. We compare it with an ACSS conductor, which is a conductor, an HTLS conductor with steel supported. Okay. These are the properties of these conductors. So you can see here, this is the section, and we compare it with the CAC of 185 millimeters square. So as before, we have less resistance. In that case, due to this wind speed, the section or the diameter is getting really important. And you can see here that even if we start with a higher initial tension, so you can see here how the CAC has higher initial tension, even though our solution, the copper microalloy solution, has 10% less tower tension, less UTS, and has more than double ampacity with the same sag. So this would be able to cope N-1 solution. So this is a really interesting solution for these wind speed cases. So the top challenges that was facing, or the two points that I mentioned before, with these business cases, I think that the copper microalloy conductors are facing these two. We can increase the electricity demand without increasing the investment, without having problems of right-of-way. We are giving solution as well in the extreme earth and space weather. So the answer is yes. We can face these two top challenges with the copper microalloy solution. Thank you very much for your attention.
Okay. Okay. Thank you very much, Gustavo, for this interesting presentation. We would like to ask our audience now to